Hello, nice to see you. I'm on board.
Excellent. So you are on board. It is 3 o'clock in view. We will start very soon. And before the chairperson will start, I just want to use this occasion also to say hello to all of you and to introduce you today's chairperson. That's Professor Ralph Kanna, who is from Coventry University and who is our long-standing collaborator and our good friend of our institute. Moreover, he is Doctor Honoris Causa on our institute. And he heads one of the largest statistical physics group in UK, which is in Coventry, and we are happy to be with them. His field of interest is field theory, statistical physics, complex systems. And personally, for me, it's I will share with you one more kind of joke, that one of things he is doing together with colleagues is application of complex network theory to analyze social networks of characters in mythologies of different cultures. And that's the reason why his students and his friends would call him also the father of mythomatics, not mathematics, but mythomatics. And one more chairperson is Dmytro Shapoval, who is almost doctor because he will and I'm sure he will submit his thesis for defense in June. He is in our institute, very active physicist. Also, he is member together with Oksana and with Mariana of the junior laboratory. They got grant for 2 years to have the junior laboratory in our institute. And his field of research is phase transitions, criticality in disordered systems, and diffusion control relations. So with all that said, I give the stage to the chairpersons.
Thank you very much, Joko. And may I ask, Joseph's talk is being recorded, is that correct? So we can...
Yes.
Very good. Great. Okay, so it is my great pleasure to introduce Dr. Joseph Yose from Coventry University, also from Minitab. And so Joseph did his PhD, did his bachelor's degree and PhD in Coventry University. I was very fortunate to be supervisor because he was a real pleasure to work with and still is. So Joseph, an excellent, really excellent student, an excellent PhD. Joseph's PhD involved the type of thing that Jurko was explaining there, mathematics, so applying maths to mythology type things and so on. And Joseph did the amazing phase transition of going from there into industry and actually that type of weird mathsy stuff and applying it to industry in an extremely unique and interdisciplinary and beneficial way. And if anybody was at, I asked a question in one of yesterday's talks about impact of our work on the outside world. Joseph is crucial to the impact that we make. And this has been crucial for the existence of our research center and our statistical physics group. And by the way, Jurko, when you said that we are one of the largest, I think we're no longer one of the largest because we've lost some people recently, but we will be hiring soon. So keep an eye out if anybody wants to come to Coventry. There's always space for good people. Anyway, that's enough. So I'd like to that's Joseph. Joseph will tell you a bit more about what he does. As I say, he's moved from the academic sphere to the industrial sphere, but kept feet in both. And he continues to work with us. We continue to write papers together. We've got 2 papers under review at the moment, at least, on funny things like that. So I pass over to you, Joseph.
Okay, thank you very much, Ralph, and thanks for the good introduction. I'm just going to show my face briefly as I share my slides with you. Hopefully you will understand why my camera is off, but as Ralph has mentioned, it's a pleasure being here. Actually, thank the team and the organizers for having me and for inviting me to this talk. I hope you can all hear me well. Let's see if I can share my slides to start off with. Let me share my screen. You should be seeing a blank or black screen to start off with. And you should be seeing my slides. Is that right?
Right.
Okay,
Yes.
that's correct.
Yes,
Okay,
good.
that's great. Thank you very much. And okay, so the setup that I've got in here, I'm not too familiar with because I'm in the office. I was intending to do my presentation at home, but it wasn't possible, unfortunately, because where I work, I'm going to explain a little bit about what I do, just to add to what Ralph has just been talking about or has just mentioned. So we have visitors today. Our CEO from the US has visited us, and we had a meeting which was meant to finish bang on time an hour ago, but it ran over by an hour. So which means I couldn't go back home to present from home. Therefore, I have to use one of the offices, and the lighting isn't that great. So I have to justify myself before showing my camera. So for those who do not know me, that's me, just so you put a face to a name. I do work for Minitab, so I'm a full-time employee of Minitab, and I work as an analytics consultant. And my role within Minitab is to work with companies that use Minitab. Minitab is a statistical software that is used by many companies in the medical industry. For those who make medical devices, it's used in research, it's used in academia, it's also used in the motor industry, in the aerospace industry. And most recently, it has been a very popular tool used by researchers and academics who've been working on the COVID test kits and also validating these test kits, and also on some medical devices and medicine itself. So what I do as a consultant is companies do come to us, those who use our software and those who may not be using our software. They've got vast amount of data, but they do not know what to do with this data. So they come to us asking for help, and they book some hours with us, and we help them look at their data, analyze their data, and look at some insights into their data. But part of my exciting work involves me working with Coventry University, especially with Ralph and team, and I'm just going to show you my team. But whilst I do that, I'm going to switch off my video camera so that I'm not sitting at an angle. Okay, so this work wouldn't be possible without a great team that I work with. These guys here, you probably know most of these faces already, but I'm just going to introduce one that may not be familiar to you. I'll introduce Maddie, the lady you see at the top here. Okay, sorry, let me just sort my pen out to start off with so I can annotate my screen. Okay, so Madeline is our PhD student. She's nearing completion now, but she works with us as a PhD student to continue with this project and some of the work or some of the research interests that we have in mythology. So again, thanks to these guys. Without them, this work wouldn't be possible. It's a great team, and most importantly to me, this team gives me a sense of belonging, especially in academia. So my research interests are in the application of graph theory, in particular network analysis, and the visualization of mythological texts. And in this work, I investigate an epic poem, which is the poems of Ossian. The origins are surrounded with a lot of controversy. But it is a very popular corpus which we cannot, or which we couldn't leave just to humanities alone, which is why we are interested in this work. Okay. Just trying to work where my mouse is. Okay. So my talk follows our paper which was published in the Advances in Complex System, and the paper was also featured in many different news outlets, as you can see on my screen. I've just shown some of them here. It's not all, and you've got a reference right at the bottom, but this is not the only paper we have done in mythological networks. It's one of many papers that we have done in mythological networks. In terms of the outlook of my talk, I'm just going to give a brief background on the poems of Ossian. Also going to talk about a couple of metrics that we can use when describing a network or when describing network topology. And next, I will discuss how network science has been applied to this particular text that we are about to look at, which is the poems of Ossian. And I will finish my talk by highlighting some of the work that we have done in the industry where Ossian has been of impact to the industry. I hope this will be of interest to you. Just reminding you guys of our opening talk on Tuesday when Oksana was reading a very interesting and welcoming talk. She did mention in the talk, or did read in the opening remarks, that the Ising lectures, they attract researchers all over the world. But most importantly, something that connects with me is what was mentioned in there, which is the fact that after the Ising lectures, some of the researchers, mostly those who will have visited Lviv for the first time, they will come back over and over again after the Ising lectures. And I'm one of them. And it's so sad that this year, I couldn't come to Lviv, even though I had planned to come to Lviv. I actually had plans to visit Lviv together with my family, but I hope that visit is going to be soon. I haven't cancelled my mission to visit Lviv, but I just hope that it's going to happen soon. Okay. And of course, whenever you've got questions, of course, we can leave it right to the end, but please feel free to jump in and ask. You can just unmute your microphones if you've got any questions during my talk, or you could just wait till the end. I know there are annotations in Teams where you can raise a hand or type in a question. If you do that and I don't respond well enough on time, please just feel free to unmute and ask, because I may not be seeing everything that is happening on my screen, just concentrating on the talk here. Okay, so on the top left of what you're seeing on the screen is the cover page of the Ossian. And from the cover page of the Ossian, we draw network properties, or we extract a network from the cover pages. I'm going to talk to you how, I'm going to explain how we do that. But having extracted a network from the text itself, we then extract some network properties which are shown or displayed on the table that you see on my screen. And these network properties, we use them to compare between texts. We also use them to put a text on a spectrum or to quantify a network. I'm going to explain a bit further what some of these quantities mean and how we use them to compare a network. But most importantly, having extracted these network properties that explain a network topology, I'm going to talk to you about some of the work that we have done in trying to use this methodology to explain or to improve a manufacturing setup where we have used this knowledge or applied this knowledge in the manufacturing industry for process optimization and also to improve product quality. Unfortunately, some of the work, because it involves a company or actual data or real data in a company, we are unable, I'm unable to share with you or show exactly some of the work that we have done. But hopefully some of the examples or generic examples that I've created here will be able to, from there, you'll be able to understand what exactly exactly we did in the manufacturing industry using this kind of work. Okay. So I thought of including a map on my screen. I know most of you guys haven't been traveling for a long time because of COVID. I'm one of them. So you may have forgotten where your geography is. So I thought I would remind you of your geography. But what you see from the screen is a map of United Kingdom. And right at the top, you would see Scotland, which is in the northernmost part of United Kingdom. And the largest part of it is known as the Highlands, and the Highlands is very rich in culture and also very rich in medieval heritage. And this is the place where the text, the poems of Ossian came from, and this is the place where everything happened. And I'm going to talk about it again on my next slide. Okay. So the poems of Ossian were published by James Macpherson, and this was over 250 years ago, about 260 to be precise. And this guy, known as a Scottish poet, who claimed these were translations into English from ancient Scots sources. So he claimed to have gone up in the highlands, up the mountains, and he claimed to have picked these scrolls and translated them into English. The poem Ossian is based on a character also known as Ossian, and this character is a legendary bard whose name is also shared in Irish mythology. We need to understand and remember that this text was written after Scotland had lost a battle to detach itself from Britain. Some of you, those who are familiar with their history, you would know that I think it was around 1746 when this battle happened, and this text was then written around 1760 after Scotland had lost a battle to detach itself from Britain. And during that time, there was also a ban that was imposed on the Scottish language known as Gaelic. Okay, and this language was used in schools, not only in Scotland, but around Britain. But then a ban was imposed to ban this language, or to ban the Scottish language around Britain. Therefore, the text was then viewed as an attempt to bring Scotland back on the map, and it actually did. They managed to meet that objective, if I may say. But the work was received very, very well internationally. The work was also, the text was also translated into other European languages. It influenced and inspired the development of other areas in narratives and in mythology. It also inspired the development of Romanticism, and the work also was compared to other classics, including the Homer, that is an ancient Greek author who's an epic poet who is behind the work of the Iliad and the Odyssey, which is also other texts that we compare in this work. We know also from history that Napoleon is said to be a great admirer of Macpherson's work. We read that he used to take this book to some of his campaigns. We know that he encouraged some of his warriors to read this text. Apparently, Napoleon's French copy is preserved in the collection of the National Library of Scotland. So if you want to see Napoleon's copy, physical copy, I'm sure it's still there at the National Library of Scotland. Okay, as I've mentioned, these were translated into other European languages. So Napoleon had his French copy, which he used to walk around with. And someone who was close to him once mentioned that Napoleon actually used to walk around with this text in his pocket, and during some battles that he was involved in, he used to go into those battles with the text in his hand, because he thought it was an inspiration to whatever he was doing. So in other words, the high society couldn't get enough of this epic poetry. It absolutely electrified European cultural life. Okay, so it was a very popular and important text, which brought Scotland back on the map around that time. However, despite the greatness in this text, this epic aroused a great authenticity debate. There were critics, contemporary critics, who had a view that this work wasn't authentic, and they thought that the work mirrored a contemporary style, which was a mismatch on facts that Macpherson had in the poems themselves. The argument is that such contemporary style of writing couldn't have come from such a distant past, considering how long Macpherson thought, or Macpherson, or how long the period that this text actually talks about. The language and the way the text was written couldn't match such a distant past, which then gave good ammunition to those who critiqued Macpherson's work. On the other hand, in Ireland, they also claimed that the work is a misappropriation of their heritage. They claimed that the story was stolen from Irish cycles. So one might think, could it be that Macpherson, also a poet himself, had adopted Irish folklore to create these Scottish legends that he thought would be taken seriously by the British elite? Who knows? Because he knew that the British elite were already obsessed with the classical Greece and Rome mythology, and which is why some of his work were compared to Homer's work as well. The work was also described as the greatest ever literary hoax to have ever existed during that time. So there was a great debate on the authenticity of this work. So our paper is an investigation using network theory, and we are looking into any clues of whether the corpus resembles the work of Homer, from which it is compared to, or whether it's a misappropriation of Irish heritage. And if we look at some of the characters that are in this text, we notice a few interesting things from the text. So a comparison of the poems to the Irish mythology supports the claim that OSSIAN'S poems were corrupted versions of Irish mythology. In Irish mythology, we have a character called Ossian, as you can see on my screen. So we've got a character called Ossian in Irish mythology, and this is a warrior poet of the Fenian cycle, who is described also by Macpherson as an uneducated bard of the illiterate age, whose father is Fingal, who is a 3rd century Scottish king, was also comparable to the Irish leader of the Fianna called Finn. Okay, so you can see some similarities in names that were slightly changed to fit Macpherson's aims and objectives. In Irish mythology, we also have this well-known hero by the name of Cuchulainn, was also misappropriated by Macpherson, also included in the poems of Ossian as the general or chief of the Irish tribes. And you can also see the differences in name and also the similarities in their names. So you can see how the argument came about and how some of the scholars actually thought that Macpherson's work was a misappropriation of Irish history. Okay, so what are our aims and objectives in this paper? So in the paper, our aims and objectives include the following. We want to determine any resemblance of the poems to either corpus from the network's point of view, to see on a spectrum between the Homer's work and the Irish mythology, where these ocean papers lie between those two corpus. Okay. We also present an investigation based upon a mathematical approach. Some of our speakers here mentioned about network theory. I think on Tuesday there was a talk about, or an introduction to network theory a little bit. I'm going to talk about it again here. That's the approach we use here to see if we can look at the structure within these texts to see where on a spectrum they lie between the Greek or the Irish. Okay, so we look at the social network structure of the poems with the Homer's epics and also compare them to the Irish text, with which comparisons have been made before. So what is a network? A network is simply a collection of nodes. And the nodes are these dots that you see on a network here. I'm not going to talk much about them because I'm sure some of you know what a network is, and you were also reminded on Monday. And these nodes, you notice that they are all joined by a line, which we call an edge. Okay. And there are a number of, and this network or this system is in such a way that we can look at the topological characteristics that explain this sociological system, or we can look at any connections between it be computers, people, or anything that has a connection. We can represent it as a network, which is what we're going to do in this particular work. And I'll talk to you or mention how we do that. Just going through some of the network metrics that we use to describe a network. One of them, most important one, is the node degree, which we mathematically denote by Ki. Node degree is simply the number of edges that emanate from a node. Okay. For example, if we look at a Facebook network, for example, say this is me, this is Joe, okay, and you look at the number of friends that I'm connected to, okay, or the number of researchers that I'm connected to. So in this case, if I'm connected to, say, 4 other researchers, this then become my node degree. Okay, so the node degree for Joe will be 4, which is the number of edges emanating from a node. Okay, we then calculate what we call an average degree, which describes a system or which describes a network. Okay, and it's simply the total number of edges in a network divided by the total number of nodes that we have in that network. And mathematically, it is calculated by this quantity that you see on my screen here, okay, represented as K. One of the most important characteristics of a network is what we call a degree distribution. And degree distribution of a network governs the probabilities for nodes to have certain number of edges within them. Okay, and we know that complex networks tend to be right skewed, reflecting the small probability for a node to have a high degree, and vice versa. In other words, all we are saying is that lots of people have very few friends. Okay, so lots of people have very few friends, and vice versa, which means a few people have lots of friends. Okay, and you can see we are mostly interested in the tail of that distribution. Okay. Just to mention a few more before I go into the results of this network. One of the characteristics that also defines a network is what we call a path length, which relates to the idea of 6 degrees of separation. In other words, there are 6 hops between you and a random person. Okay, so if we take you to be here, for example, there are only 6 steps between you and a random person. Okay, so if there is a random person here and there is you here, we only have on average 6 steps. So we are connected to Joe Biden, for example. If I'm to pick that as a random person, we're connected to Joe Biden by only 6 hops. Okay. Another important quantity is clustering, which is based on triplets of nodes. For example, I've got a small picture on my screen, and this measure looks at the concentration of a node's neighbor. In other words, it looks at the cliqueness, or how a node's neighbor forms a clique. Okay, so for example, if I'm to look at node B, you notice amongst the other 3 nodes that we have, there is a clique or a triangle between node B, C, and D. In other words, there is one triangle that is going through node B, but if we look at the whole network, there is a possibility of, or we could have 3 such triangles in this node. Therefore, we can define the clustering or cliqueness of node B quantitatively as 1/3. Okay, we have one triangle or one clique out of a possibility of 3 cliques, and mathematically it's calculated as what you see on my screen. We are interested in average values, therefore we calculate the average clustering of a network. Having calculated the clustering of each node, we then calculate the average clustering of a network, represented either by C bar, or sometimes you see a C hat on some of the network parameters. Okay. Associativity is the tendency for similar nodes to connect, and it captures the degree-to-degree correlations, and this quantity ranges from -1 to 1. And if a network has this associativity, which is mathematically denoted by R_K, if it's negative, it means a network is dissociative. Okay, it means the network is dissociative. And if it's positive, it means the network is associative, which means like similar nodes tend to connect with other similar nodes, or vice versa. Okay. Okay, that's that done. But we also need to remember that we address the totalities of these relationships between characters. We are not really focusing or interested in individuals. We focus on the totality of the network. Therefore, if there are any small deviations to the amount of nodes or amount of edges in a network, it doesn't affect the network statistics that much because we're interested in the averages or the total relationships in the text. Okay. So what in this particular text, what we did is we took all the characters, and the characters in the text represent the nodes in a network. And an edge was formed where 2 characters interact with each other. So when 2 characters come into contact, whether 2 characters are involved in a conversation, we created an edge between 2 characters. I'm sure you would understand that there could be 2 types of edge. One edge could be directed in the sense that, say, for example, if I am to make contact to someone, it could be a directed network or a directed edge in the sense that the contact is from Joe to a particular person. But in this case, we treat our network as an undirected network, which means whenever person A makes contact with person B, we also take that to be vice versa. Therefore, the node degree for node A in this case will be 1, and it will be the same again for node B, which is a bit different to a directed network, which I'm going to look at when we are looking at how we use this to solve a manufacturing problem, because that's a directed network. I'll come to that in a bit. Okay, so that's how we form edges, and our edges are also characterized into either friendly network or hostile network. Okay, so where we have characters meeting in combat, or where we know there is hostility between two characters, we classify them as a hostile network. Okay. And where we know two characters to be friendly with each other, say, for example, they're just involved in a conversation, or they are related to each other, or we are sure they know each other, we classify that as a friendly network. Okay, so we also analyze our network into these two categories, hostile or friendly networks. Okay, and we also look at the network as a whole with both edges included in the network. Okay, and one of our some of the things that we're interested in a network, we calculate them from what we call a giant component. Okay. So a giant component is in itself a connected network. So you can think of a network having several characters, but within these characters, some characters may talk to each other, but you may have within the same network a certain group of characters that probably do not talk to another clique or another cluster of people. In this case, we will be having two components in a network, and the biggest of these components is what we call a giant component. Okay, so it is the one that has the greatest number of nodes and connected, and is mathematically denoted by GC. So if you see this quantity in my analysis, that's what we are talking about. So enough about network theory. Let's go to the poems of Ossian, and look at how the network looks like. As I've mentioned, we took all the characters in the Ossian network, and we created edges between them where they communicated with each other, or where we are sure that they know each other or met in combat. In the network, we also excluded isolated nodes, that is, characters that are mentioned in the text but do not appear to be in contact with any other character. So these isolated nodes were removed from the network, so that you know. But most importantly, we looked at the giant component. Our giant component in this case for the Ossian poems, and also for the other texts that we use to compare the Ossian, were all at least 80% or contained at least 80% of the nodes. Okay. So it makes sense for us to just analyze the giant component in this case, as it constitutes a greater number of characters in a text than the other smaller components in the network. Okay. We noticed also from our analysis that most of the stories from the texts that we have looked at so far are mainly driven by positive interactions. We noticed that out of both hostile and friendly edges, 90% of all the links are most likely to be friendly links than hostile links. Okay, so in some cases we will just analyze the positive network, or which we also call a friendly network, which we also call a positive network of a giant component. Okay, and what you see on my screen is the OSSIAN network with each dot representing a character, as I've mentioned, and the link between them representing nodes that know each other or that connect with each other. The blue edges represent the friendly links, and the red edges represent the hostile links. Okay. Let's look at the statistical quantities that we extract from the network. So we compared the OSSIAN network to the Irish text, as I have mentioned, that there was a big debate as to how Macpherson might have obtained his text, and some scholars believe that this was a misappropriation of Irish texts or Irish mythology. Therefore, we compare the OSSIAN poems to one of the Irish texts known as a column. Okay. Why this particular text in Irish mythology? We have what we call the Fenian cycle of Irish mythology, which has a format mainly of which has a poetic format mainly, and these are known in Irish mythology mostly as texts that play out in Munster and other eastern and southern parts of Irish provinces. Okay. So that's why we compared them to the Akallam. Okay, one of the most popular texts or most popular mythological text in Ireland. Okay, and this is one of the texts where some of these characters that we saw between Ossian and Irish mythology came from. Okay, we also compared it to this text to Iliad and Odyssey, because we know that Macpherson's friends, including Macpherson himself, compared his work to Greek mythology. Okay, so some scholars and his friends claimed that his work was inspired by Greek mythology. That's why we compare the work to the Irish and also the Greek. Lady Gregory is also part of the Fenian cycle, but came out a little bit late than the Akallam. We simply want to use this text as well. It's a very important text, as we know that some of the scholars argued that James Macpherson used some of the contemporary writing in his work. So we also wanted to compare it with one of the contemporary writings of Irish mythology, which is the the Lady Gregory. Okay. And looking at the network statistics, N is the total number of nodes in a network, and these nodes are positive, come from a positive network, or the giant component of the positive network. We also have M, which represents the total edges in a network. But as you can see, the two are not of the same scale. Therefore, we look at the average degree to compare between networks. But as you can see from the average degrees, the network statistics doesn't show much difference between them. Of course, you may notice that the average degree for Homer's texts seem to be a little bit higher compared to the average degree for Ossian and some of the Irish texts. Okay, so maybe if you want to, you could maybe look at these differently, but they don't seem to be statistical significant. They don't seem to be a significant difference statistically when looking at the average degree. So we cannot distinguish between these narratives by just looking at the average degree. Also, when we look at the average path length, maybe should have included that as well, just to show it's an average path length. You also notice that the networks seem to have almost the same average path length, again making it difficult for us to distinguish between between the texts, and we also look at the clustering coefficient. Again, you notice it's almost the same, and if we look at RK, which is the associativity, again you notice they are mostly dissociative, meaning that nodes of higher degree seem to associate mostly with nodes of lower degree, apart from the Iliad, which just has a slightly positive associativity compared to the others. So looking at the network statistics, nothing much we can use here to distinguish between the characters. But again, a high clustering coefficient and a lower path length shows us that these are small world networks, which resemble some of the real world networks that we have observed in practice. Okay. Any questions so far? Okay. So
there was, I saw Olesia has raised her hand.
Okay, thanks for that, because I couldn't, I haven't looked at the chat so far. Thanks.
Yeah,
Jacob.
Thank you.
Yes,
I just wanted to ask about this table. I noticed that there is a difference between clustering coefficient and transitivity for Gregory and the ask alarm.
Okay, I can't. Your line is breaking, Olesia.
I think the question was about how could you comment about the difference between the number of triangles and the clustering coefficient. Probably Olesia meant that it is an evidence of some structures, communities present in your network, right, Olesia?
Sorry, something is my connection. So I just wanted to ask about these two columns, the clustering coefficient and the transitivity. And for some rows, we can see that the values are very close, and for some rows, we can see some larger difference. Do you have any interpretation for this?
Okay, yeah, that's a good observation, because clearly you can see from transitivity that the OSSIAN and our column and all the others are below 40 or below 30. But if you look at Iliad and Odyssey, it's a little bit higher. However, there is both of these quantities explain how clustered a network is, but one clustering looks at just the triangles, looks at the number of triangles as I've shown earlier, and transitivity also looks at how a node is involved in other connected nodes. Okay, so in the Iliad, you notice that the clustering is a little bit higher compared to the others, of course, but this is just one out of many quantities. So, of course, there seem to be an inclination here that the OSSIAN is different to the Iliad, and yeah, here maybe to the Iliad, because the Iliad has a higher clustering transitivity compared to the other two, but you could put it similar to the column. However, we didn't do a statistical test to check a significant difference between transitivity, but it's probably something that we can also do to check if, of course, we can see there is a difference, but is this difference something that we would expect by random chance, or is this difference a big difference that actually tells us that there is a significant difference between the text? We didn't go that far, but of course, it's a good point that clustering transitivity for the Iliad is slightly higher, which means in the Iliad, they seem to be big clusters. We also need to remember, or maybe not remember because probably you might have not read the text. But in the Iliad, there's something special that happens in the Iliad. In the Iliad, we've got a group of characters. I can't quite remember the actual number, but it's quite a big number of concern. I think it's about 17 characters from the top of my head, but I stand to be corrected, but somewhere around here. So these characters, 40 characters, I think, 40 characters. So these characters appeared in one meeting together and they seem to know each other, therefore giving a clique of these 40 characters. In other words, all these characters are connected to each other. Well, don't quote me on this number. I think it might be wrong. But anyway, all I'm saying is there is a big group in the Iliad that seem to know each other. Therefore, that inflates this number here. Okay. But when we remove that click or that number, the clustering transitivity seem to go around the 0.3 as well.
Thank you.
Okay. Okay, is that another question?
Yes.
I see that Reinhard has a question.
Okay, yes. Yeah.
Yes, I have a maybe a more fundamental question.
Okay.
How you get all these numbers out of the text? I do not think that you have to read it personally, although you would do, but you have to judge, for instance, if some connection is friendly or not. How do you do that?
Okay, very, very good question. So in this particular work, because this was part of well, it's part of our initial project to analyze textual information using social networks. We had to make sure that there is a method that we are familiar with, that we all know, a method that will also be acceptable by the humanities people. Remember, this kind of work is mostly the work of the humanities experts or researchers. So they don't really like us mathematicians going into their area and converting all texts into numbers. So in order for us or for them to accept our method, we had to use a method that is acceptable by both, by reading the text. So actually opening the text, reading a text, and with a few rules, we have a few rules that we have defined as to what constitutes a link and what constitutes a node. A node is a character, and a link when we are sure from the text that two characters, they talk to each other or they are related in some way. However, that work is now being taken further by our PhD student, Madi, the one that I've introduced earlier, to see if we can find a way to automatically look at a text and extract nodes from a text and also add edges to that text automatically. And she's doing a great job so far. So she's going through all these texts and doing that. And I should mention here that keep your ears on the ground. Hopefully we'll get to publish on that work. So we are working on getting it done automatically. And in fact, just to add to that, we actually have a manufacturing company that looked at this work, and they asked exactly the same question that you have asked, and they are interested in us looking at the research papers that they have written on their work, on their manufacturing process, and create links that look at particular subjects of interest. For example, if you look at a steel making company, you will look at, say for example, another paper is to do with metallurgy, another paper is to do with magnetic properties. Can we extract these topics from papers automatically and link researchers that discuss this thing? So it's something that we are doing at the moment, but not published as yet.
Thank you. Thank you.
Okay. Sorry, long answer, but yeah. Okay, that's great. Okay. So let me quickly go into how we compared these networks. So as I've mentioned, from the quantitative properties or measurements, we couldn't distinguish between the networks. So we used the degree distribution, as you can see on the degree on my screen, on the left-hand side of my screen. Excuse me. You have the degree distribution for the OSSIAN network compared to the Irish mythology, from which scholars thought the James Macpherson misappropriated their history. Okay, and you can see from the degree distribution that the three distributions almost overlap each other. You notice that the degree distributions are almost the same. And if you look on the right-hand side, we also compared the Ossian to the Iliad and Odyssey, from which James Macpherson himself, including some of his supporters, think came the inspiration to look at this work. Okay, and we notice differences in degree distributions between Ossian compared to Homer's Iliad and Odyssey. Okay. This is what our eyes see, but what we also did, we quantified these observations by looking at one statistical test known as the KS test, or Kolmogorov-Smirnov test, which is one statistical test that doesn't assume distribution. So it's a non-parametric test, and it looks at the shapes of the distributions. Again, as I've mentioned, it doesn't assume any distribution when you're using it. So we found it to be ideal in this particular instance. And these tests, the results from these tests, we use probabilities, and the probabilities show that the networks that you saw on the left-hand side are actually similar, and the networks on the right-hand side are actually different. Okay, I thought I printed the probability values for the networks, but probably something that I missed out. Okay, I notice I'm only left with a few minutes, so I'm just going to be quick here. So one question that our PhD student, Madi, is also looking at what we call network spacification, also known as network sampling. Okay, so this is the same as network sampling. Okay, and looking at these texts, if the results are showing that the Ossian resembles the Irish mythology than it does the Homer, if we are to imagine in our head, imagine that Macpherson had the computational power that we have today. Imagine that Macpherson had these methods that we have today. How could he have done it? Okay, if he knew network theory, how could he have done it? Okay, so we're looking at network specification or network sampling. Why? Because the Akalam, which is the Irish text that we are comparing Ossian to, is a bigger network. It has over 500 nodes, and the Ossian text, the one that James Macpherson worked on, had approximately 260 nodes. I'm only talking about the giant component here. So because of this, we're trying to see if there are any methods that we can use to sample this bigger network to obtain the Ossian. And we noticed from our work, we tried some random selection, a random walk, for example, and we noticed that none of the random methods work, which means it wasn't a random thing that happened. It's actually a probabilistic way of doing things. So I'm going to leave that to Madeline to talk about later when she's done with that work. I'm not going to go deep into it, but we found some statistical or probabilistic methods that might have been used, or that might help us explain what might have happened for James Macpherson to come up with the text that we are looking at. Okay, So just to conclude on the work of OSSIAN, we notice that the network of OSSIAN resembles that of Irish mythology, that is Akalam, Naseronach, and probably mispronounced that, but I'll just call it Akalam, and the Lady Gregory. And we also notice that the network of OSSIAN is different to that of Homer. This means that while some of the names may have been changed, as we noticed in the other table that I've shown you, the social networks of many of these characters were kind of the same, something that is unlikely or less likely to happen by chance. It is possible that Macpherson might have used some of these methods, or maybe these methods help explain what may have happened between those two texts. Okay. So how does that impact on a manufacturing process? Let me just talk briefly about one of the organizations that we've been involved in. Okay, this organization is a steel industry. Unfortunately, I'm not going to mention the name, and I'm also going to be just generic about it. I hope you understand why. I'm not going to talk about the steel making process. Some of you might be aware, maybe from school, so I'm not going to talk about that. But this simplifies the process. So here we are looking at just three main inputs that go into a blast furnace. First of all, we've got what we call a sinter plant, which combines the iron ore with limestone to create what we call a sinter. A sinter is something that looks like a rock, which is something that needs to be digestible by the blast furnace. So this is heated at some temperature, making sure that the sinter doesn't liquidify. But the size of this sinter is very, very important in the steel making process. So lots of parameters go into this sinter plant, quite a number of them. I'm going to maybe highlight some of them in a bit. But the size of the sinter, the size of the stones that come out of the sinter plant are very important in the blast furnace, because they do affect the quality of what comes out of here. It affects the quality of liquid steel, and in turn also affects the quality of the final product that go to the customer. Okay. So when it comes to tracking a material, just imagine this in this modern day, that we have a manufacturing company or a motor industry manufacturing company. So they make cars, and within their factory, as you know, there is a big drive in electric cars. And a big drive in electric cars is also affected by the battery performance. We know at the moment that the batteries that we have cannot propel a car to such a distance that is comparable to a diesel car or a petrol car. And one of the factors that affects the distance covered by a car with the current performance of the battery is the weight of the car. Therefore, there is also a high drive in what we call light steel. Okay, there is a very high demand on light steel. Okay, it needs to be light so that the car is light, so that it can go a long distance. But also one of the factors, you would know that in addition to having electric cars, there is also a drive for autonomous vehicles that can drive themselves. Therefore, it's important that we make sure the material used to make these cars is strong, which then increases the demand, or which brought about this new product, high strength light steel. Okay, high strength light steel. Okay, two things that contradict each other. Therefore, if it happens that the material go to a manufacturing company and they notice that the steel hasn't got properties that supports these two objectives, we would want to know what parameters in this process we need to change in order to improve the quality of the steel. Therefore, it's important that we can track the, say, for example, there is a defect on this material. We need to be able to track where this defect came from in the process and hopefully correct that property that is lacking or that brought about the defects in the process. Okay. At the moment, or when I joined, we could only track material from casting, okay? When where we've got a steel slab. So a steel slab is a physical product that you can actually see. It's a solid product, whereas in the ladle, this is liquid steel. It's a slag, and we know that a full ladle, in most cases, a full ladle will go into casting a certain number of slabs. So we can actually track a slab to the ladle that was used for that particular product. Okay, that was just a simplified figure. Looking at a bit more complex one, I'm sure you can see. So this is where the steel ladle is, the one I was talking to you about. From the steel ladle, once it's solidified, it goes through casting, it goes through, and in casting, it's rolled. So it's hot rolled, okay, to change some of the mechanical properties of the steel. Some of you might be familiar with the process than me. I'm not an engineer, I'm just a number cruncher, okay? And when the steel is rolled, when it's rolled, when it goes through the rollers, when it goes through the furnaces and stuff, at most stages, the steel is made into what we call a coil, okay? When it's rolled, it's made into a coil, okay? You'll probably see a picture soon of what a coil looks like. Then this coil is transferred to the next process, say, for example, cold rolling. It's also cold rolled. Then it's also put back into a coil, and this is transferred to another process and so forth and so on until we reach to a final product. It be coil, a strip of coil, which then goes onto a car, or these may be bars of steel or whatever it is. Okay, so at each process, there are a number of mechanical properties that we look at, some of them listed here. I'm not going to talk about them for the benefit of time, but we want to know the length of steel. So, for example, the steel slab might just be 9 meters in length, 9 meters in length, but it may have a thickness of, say, for example, say 50 centimeters in thickness, and it goes through rollers until it reaches a thickness of a razor sharp of 3 millimeters in thickness and maybe reaches a length of 3,000 meters. Okay, something like that. Okay, don't worry about the numbers. Okay. Okay, so that's what happens. And at each stage, when the steel is passing through the steel making process, we collect a number of variables. Okay. And the last time I worked with this data, I had approximately 400 variables that are involved in the mechanical properties or in the quality of steel. So quite a number of properties that you can optimize on, or that you can use some machine learning algorithms to optimize on the quality of steel. Okay. However, these properties, or before I go into them, some of the most important ones are the thickness across the width of the sheet. We'll call this a sheet. We're interested in the true width. We're interested in whether there is a crown or not. We're interested whether there are ridges in the coil. We're interested in the shape. Are there any contours on it? We're interested in the flatness of the coil. We're also interested in the speed at which the rollers are going as the strip goes through different processes. But there are many different things we also need to consider. We also need to consider some swaps and turns, or head and tail swaps, top and bottom swaps, as a coil is moved from one process to the other. So say, for example, I've got a coil that looks like this. Let's just simplify it this way, okay? But this coil is made out of two parts, okay? There is one coil in blue and another coil in red, and these two coils are welded in the middle, okay? If going through the process, so sometimes we pass it on to a different machine, which then coils it in a different order, okay? So in this case, if we uncoil it this way, we're going to end up with the blue in the inside, and we're going to end up with red on the outside, okay? Or sometimes this coil is passed on differently, maybe at the top, okay? Or sorry, maybe at the bottom, like that, sorry. Is that the same? Okay, like this, okay, which then converts the top side of a coil. The top side of a coil becomes the bottom side of a coil as it is rolled. As you can see here, this means the top remains the top as it goes, but when we roll it this way, it means the top side is getting into the inside, becomes the inside coil. And again, the tail, when it's rolled, becomes the head, when it's unrolled, becomes the tail in the next process. And the processes are many, and you can then imagine when the coil gets to the end of the process, to know at this stage what has happened at this stage, whether this part on the process, or where this part is on the final coil that goes to the customer. So those are some of the complexities that we had. Again, here, some of the complexities mentioned. We have different processes to produce different types of steel, and they have different chemical composition and different mechanical properties. And it also depends on whether this material is made for packaging, medical, or automotive. We need to also remember this is a continuous process. The line runs 24 hours a day, 365 days in a year. So very difficult. There's no way you can stop a process and have a look at what's going on. It's a continuous process, making it a non-trivial problem. So what is the problem with all this? Okay. Okay. Questions that we want to answer. Say, for example, there is a customer that has called us that bought our product, and they've got or noticed some defects in the product. We would want to be able to detect all the other material that is the same before it goes to the customer. But you cannot do that if you cannot identify those coils or that material that may also be defective. Apart from that, we would also want to correct that problem by identifying the source of the problem. But you cannot do that if you cannot track or trace the material to where the problem comes from. And therefore, our idea or what motivated this work is the fact that we could use the same mapping that we used for the OSSIAN network to look at the manufacturing process, whereby a node in this case is represented by a material ID. So say, for example, you've got a certain part. This part has a part number associated with it. But before this, we also need to remember that a part number was originally given, or before I joined, was originally given in ascending order from 1 to the last part produced. But a machine can also take up to a certain number of digits. Say, for example, it can take up to, say, 6 digits, okay? Which means the numbers would wrap around in just 1 month, okay? making it difficult between two parts to distinguish a part that was made yesterday, that was made last year, to a part that was made today. So one thing that we did to cater or to cover that problem was to give a prefix to each ID, a prefix that identifies the process. Say, for example, this is hot rolling. We'll give a prefix H and we'll give it a number, which is the part number. But as you have noticed with the problem that part numbers would wrap around after every year, we also added a suffix to this number, a suffix which is a timestamp at which the part came out of the process. Okay, so we could give a year, a month. We know that parts wouldn't wrap around in a month, so a year and a month was just enough to add to the part number, which made the part number unique and also made it possible for us to use network analysis to look at it. But you can also think of other problems where we have reworks. Say, for example, a part has gone through one process, or cold rolling, for example. And when we get to this end, we do a test and we notice that we didn't quite reach the thickness that we require. It will then go back to the process and it will be rolled again until we reach the correct thickness. And we know what these loops bring to a network in terms of complexity. But this way of numbering our coils made sure, because there will be a different timestamp, made sure that we don't have loops in our network. I think the resolution, we ended up to hours. I think the resolution was up to an hour. Okay. The other problem is we don't have straight routes. Okay. Thousands of processes and machines included, reworks and splitting of coils, and also some coils being joined. All this presented problems to us. Because of time, I'm not going to talk much about it, but also go further. But all I can say is from network analysis, we could map these manufacturing processes, or we could look at a manufacturing process using a network analysis approach. And it made the tracking of material quite easy and simple. Not only the tracking of material, it also made the querying of data much simpler and easier. I'm very mindful of time here, so I'm rushing. I didn't realize I needed more than an hour. But anyway, imagine a situation whereby you're trying to check where this particular coil came from. In a network or in a graph, you can easily check or search for this network, and it will give you the lineage of this network. By the way, this is a directed network and also a hierarchical network. And the good thing about representing this problem as a network is that on each node, as we have done with the OSSIAN network, we could add node attributes to the network. Okay. In the case of textual information, a node attribute could be the gender of a character. A node attribute could be the page number from which the character was identified, or a page number from which an edge was created. It could be a faction where this node belongs, or it could be a family or a group from which this node belongs. Taking that to a manufacturing process, an attribute could be the temperature at which this material passed through this machine. It could be the temperature it passed through this machine. It could be the time taken for this process to finish. It could be the tensile testing that has been done, or results from tensile testing that has been done, results from back hardening tests that has been done, and so forth and so on. Therefore, in the end, we could look at parts that pass our quality tests, or pass parts that have defaults. Okay. For parts that have defaults, we could then use this network approach to find a lineage or to find a route that results in more defaults than other routes. Once we do that, we can then use some machine learning algorithms to find the properties at that root problem point, properties that influence the defaults or properties that influence the quality of that material. And this can be done automatically. And I'm going to just show you as I finish here. Just bear with me 1 moment. Ocean network. Okay. And in the end, what they have or what they are currently using is something that looks like what you see on my screen. So this comes from an OSSIAN network. So from the OSSIAN network, we created an interactive network. And from the interactive network, you've got the key here. So please feel free to read this at your leisure. But I'm going to add here in the chat, if I can find it. Okay, I'm going to add a link to this through the chat. I'll do that at some point, maybe when you're asking questions. But so each dot here is representing a character in the OSSIAN network, and the link, as I've explained. So you could click on a character here and zoom into a character, including the a component that connects this character to the first degree, second degree, and so forth and so on. This just connects to the first ego network for that degree. And you can also see other characters that are connected to that particular node. You could also search a character. So for example, I could search Ocean, and it will go straight to that particular character. So this is one method that we also employed in the manufacturing industry, where if they want to query a particular material, they could just type the part number here, and once they type the part number, they will then see that part number, including the lineage of from which the part came from, and with that they could also see the properties of that node. It be the temperature instead of the giant component here, it be the length, the width, etc., etc. So it then, this method has simplified the way they look at quality. It has simplified the way they look at their materials, or the way they look at the lineage of their materials. And this work, I should mention also that it has saved the company millions of pounds, and also a vast amount of time, which we can also quantify in terms of how long it used to take someone to look at a problem given a particular material ID. Now they can do it just at a click. The only challenge we have that we are left with is the size of the network. The network is very, very large in such a way that what happens behind the scenes, or the codes that are used to create a network, are slow. Of course, the network is the network is run every night, but it takes several hours for the process to run. So that's the only challenge. So if you've got any ways of analyzing a very large network, I'm talking of a network that has over 50 million nodes and many edges here. But so far the method works. But if there is anyone who knows an efficient way of looking at very large networks, that would be greatly appreciated. Unfortunately, I couldn't go into much detail because of the nature of the problem, and I thought I would show you some of the real output of this, but because of time, I think I will end here. I hope you've enjoyed the talk and learned something from it. Thanks again for listening, and thanks for the questions earlier. Any other questions?
Thank you, Joseph, for this fascinating insight into that other world out there of industry and things like that. Very, very, very unusual for us to see some of that. So thank you. Are there any questions? Yoko, I think, has a question.
Yeah, thank you. Actually, two questions. The first one is very short. Did I understand properly that OSSIAN network you show here is 50 million nodes, or I just misunderstood something? Why it is so large?
Okay, yeah, sorry. The 50 million nodes are from the manufacturing problem that we are looking
Okay,
at.
thank you. Yeah. Then the second question, that's because of my ignorance. You know, all I know about Irish and Scottish mythology is because of your group, what you are doing. So probably it was easy to borrow characters from Irish mythology when Macpherson was writing his text, because the cultures are close. At least both languages, Gaelic and Irish, are from the same language group. But what about analysis of Scottish sagas? Did they exist in such a number that you can do some statistics? And could you compare, for example, properties of sagas of Ireland with properties of similar mythology in Scotland?
That's a very, very good suggestion, Yoko. We haven't compared OSSIAN to other Scottish texts, simply because the debate was mostly surrounding the OSSIAN text against Irish mythology and the OSSIAN text against the Greek mythology. Very little was said about the OSSIAN text or James Macpherson being motivated by other Scottish texts. However, it's actually a good idea to put it on a spectrum against other Scottish texts, because they are there, but just that we haven't looked at them. Not many, but they are there around.
Thank you. And thank you very much for your presentation. Thank you.
Okay, thanks, Yoko.
Are there any other questions, perhaps? I would ask a question which I find I haven't asked you before, Joseph, but generally the transition from academic world to the world of industry, did you find that a difficult transition to make? I mean, you've somehow kept very strongly in the academic world as well, but I think it's not easy to maintain a foothold in academia while you're busy with industrial things. Do you find this a relatively straightforward thing to do, or is it difficult time-wise?
Well,
culturally as well, actually.
Yeah, I'll talk about it in two ways. So firstly, when I started in the industry, there was a big, massive challenge in the sense that most of the those people interested in manufacturing, they believe that what we do in academia is just theoretical. They know that it influences what they do in the industry, but they think they've got it already. There is nothing from academia to add to what they're currently doing, which is a big challenge when you're coming to academia, to draw attention so that you can tell them of these new methods that are being formulated in academia that they could use. So with this particular work, when I started, I was actually isolated in my group, in the sense that I was given this. They looked at the OSSIAN, they were interested in it, they were interested in my talk and my suggestion that we could use a similar network interactively to look at the network of how parts connect throughout the process. So they gave me a year to work on this, but it was on the side, and it was also not part of the R&D department. It was something that was hidden, like I would say, under the table. They didn't want to talk about it because the probability of it being a failure was more to them than they thought it would be successful. But then apparently after just 2 months before my probation, they noticed it was a success. Then they started, or we started talking to other departments about it. So again, the reception of it wasn't easy. Then secondly, in terms of time, it's very, very, very challenging between industry and academia. As you noticed earlier, yesterday I thought I will have a full day to work on academic work. They gave me the time to do so. But again, a customer came. It's more important to them that they make money than me doing research. They do make money by me doing research, but because it's indirect, they prefer direct ways of making money. So those two are always a challenge. But again, successful projects like this give us strength, and they give us, they propel us a bit further.
Thank you very much, Joseph. Any other questions? Okay, so should we say thank you to Joseph again, and we can move on to the next speaker, if you like. Thank you very much, Joseph.
Now we have a kind of, we don't have break at all, and we were assumed to have 15 minutes break. If the chairperson do not mind, maybe we have 5-minute break and start 5 minutes later, just not 30, but 35, just to allow people to have a short break.
Okay.
Okay.
So we start at 16:35 in Lviv and in 15:35 in Middle European time, and so on.
Yeah, good.